Yo, yo, yo. What's up, what's up? Welcome back. Today we're working on my operating system. It's an x86 operating system written in Rust. Code is, for the most part, online on GitHub, so there's a repo at github.com/my username/streamos. And right now it's like kind of just like this kernel that runs like this demo. It doesn't really do a whole lot, but let's see if we can run it. If we get something out the other end. So we have like this thing, it pops up. It opens a QEMU virtual machine by default. I don't really know if this would run in other virtual machines. It could probably, but I bet you there would be bugs if we tried to open in VirtualBox or something, but we're probably not that far from that. We've never tested on real hardware, but and I imagine that we're probably pretty far from that working. But you know, here he's doing like a little bit of stuff. So he's like drawing to the screen. He's handling user input. So I've got like a little bit of like a shitty keyboard driver using PS2. I've got we've booted. We have like memory allocations. So we're using like vectors, hash maps, all that good stuff. We have like a clock driver, serial driver. So we're like writing logs to the serial console, which QEMU is forwarding to the standard in and out of our like just standard output of the virtual machine. We have like a whole like Ethernet stack. So if I like go to this IP, I've got like a web server running, and he says like hello from StreamOS kernel. I can say like hello from the web browser, and that he goes like, hey, I got that input. So we're running like some form of web stack. So we have like PCI so that we can run Ethernet, so that we can do like ARP, which is like address resolution. And then on top of like Ethernet, we have TCP and HTTP on top of TCP, and all that's like kind of doing something. Recently we just finished up our multi-core support. So, I'm using the word finish loosely, because it's not quite finished because our unit tests are broken in that scenario. But if I run with this guy, I'm supposed to see indication that he's, oh yeah, here we go. He's saying like, hey, I've got this request on CPU 0. And if I refresh this a few times, he'll say like, oh, I serviced this one on CPU 1. I serviced it on CPU 0. I serviced it on CPU 0 a bunch of times, CPU 1 once. Great. So he's like he's dispatching events to multiple cores, etc., etc. Anyway, so that's like the state of the OS at this point. It doesn't really do much, but it's got some of the fundamentals in place. And what I want to work on next, the next kind of like checkpoint that I'm working towards is this guy on my YouTube comments said, does it run Doom? And that is like the end all and be all of like, your thing's a real piece of software if it can run Doom, because Doom can run anything, right? We've seen that meme all over the place. It pisses me off that the answer is like, not really. And the reason that I feel like I can't do it yet is because I'm missing two things: sound and mouse. And so using the mouse, I think, would probably be like pretty straightforward using like the PS2 interface, but I don't really think that's reasonable anymore. Right? Like, when was the last time I've seen a PS2 mouse? Where PS2, sorry, we're not talking about PlayStation. We're talking about PS/2. Let's see if Google fixed this like result. When I look up PS2 name, it used to give, oh, it did. It used to give me like this pop-up that just told me the wrong thing. But anyways, it's a connector that's like kind of like serial-esque. Anyways, I could implement the PS2 version of the mouse like I did for the keyboard, and that would like be reasonable to some extent, but I don't like that I wouldn't be able to use any, like, all of my mice in real life are USB. I've at least seen PS2 keyboards. I don't think I've ever even seen a PS2 mouse. At least not in the last like 20 years. So I don't think it would be fair to implement it. So all of that to say, I would like to implement some form of USB stack. And as far as I can tell, USB looks like fucking complex. Let's look up USB on OS Dev Wiki. Right, like this is a long ass page. There's a lot of text in here. So I'd kind of like to just like start by trying to see if we can like glean any interesting info from working with the USB controller that Huimu gives us. It would be interesting to see if we could at least probe a device and like see if we see, like, I just want to like see activity. That's kind of the goal for today, is like do anything with the USB thing, with the USB, because I think that this is going to end up being like quite complicated, and so I want to set like a reasonable goal, which is just do something. And so that's where I want to go. As far as I understand at this point, I've kind of like skimmed this. I haven't really read much in much detail, but I've kind of skimmed this as well as looked at the EHCI. So, as far as I understand, hand wavy. I've got my computer. CPU. That's me. Smiley face. That's me. And as far as I understand so far, we have like, on the other end, we have like my mouse, right? He's like, wow, really pretty mouse drawing. It's a mouse, guys. It's a mouse, right? Only a mouse, nothing else. He is connected into this like USB port. Boom, 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 boom. And this goes to some like, I'm just gonna like draw a little cloud here, which is probably wrong because people draw clouds to talk about the cloud. I'm not talking about the cloud. I'm just talking about like stuff, right? Which, you know, you could have like multiple USB hubs or something like that in between, right? But mostly like eventually it comes past through all the hubs and stuff, and it gets to like this like PCI card. What do PCI cards look like again? Like something like this. And like they're like, they've got like a million pins on them and like this notch. PCI card, which is plugged into like the PCI bus. We could draw a little bus here for that, I guess. He's got little wheels. He goes into the PCI bus, which goes into my CPU. And so, if I understand correctly, this guy, he's called like the host controller. Right, and he's got like basically the abstractions, I guess, to like talk to USB devices at like the like hardware level. So instead of me having to be like, I'm gonna wiggle this wire up and down, I'm gonna, right, to be like, I want to send this command. Like if I wanted to say, I want to send a setup command. Like I think, I could be wrong here, but I think instead of me being like, the setup command has like bit 1, 2, 3, 4, 5, 6 set this way, and I need to wiggle the wire and like keep track of all the timing. I think the controller is supposed to take care of all of that for me. And it looks like, from skimming this page, the controller has like these like registers where I can write like, oh, I want to send this command, and I want to like read the status register, and I want to enable interrupts. Like, it looks like it's kind of like, calling it high level is probably a little rude to my audience who maybe considers high level like writing JavaScript, right? But it's higher level than like me wiggling bits on the wire. And so that's, yeah, what I want, like where I want to start probably is trying to get a handle to this guy, this like PCI host controller, or sorry, the USB host controller, which is a PCI device, and maybe seeing if we can like find a device on the USB bus in some way. And probably we're going to hit some snags along the way, and so we'll just kind of like start plowing through them as we go. You could argue that I should be more well-read and I should understand what the process is to get there, but I guess this is the way I work. I find it easier to understand things as I go than to like get a big picture up front, because often the big picture I get up front is just totally fucking wrong, and I can't really like hold focus for that long. So this is easier. So the first thing we want to do is get a handle to the USB host controller. Or maybe find it is a better way to say it. Find the USB host controller. Okay. So how do we do that? So USB, they have multiple iterations and multiple protocols for how you talk to the host controller. And if I understand correctly, each like new version comes with like new speeds, right? You have like USB 2, USB 1, USB 3, and each one will get brought like a big bump in throughput. And so I assume that we had to make new protocols to talk to these like higher speed devices, because like how you interact with a thing that can go faster is more complex, generally hand wavy, right? And so instead of handling that all in the controller, there's like more things that we have to do in software, and so we need to use different protocols. And so what I want to do is I probably want to start with USB 2.0. I think probably I don't have to deal with USB 3.0 because like the speeds that you get out of that are like gigabig, right? Like they're like for like data transfer and USB drives and stuff. And I think that like most mice I've seen are probably still USB 2. Like if I look at like, I don't know, like if I look at like the G Pro wireless, does it say like specs? Does it USB? It doesn't say if it's like USB 3.0 or USB 2.0. G Pro wireless USB 2. Does it say? Or 3. You will gain no extra benefit by using 3.0. That's kind of like, yeah, kind of what I thought, because your latency is probably the same, but your throughput is big, but like your mice aren't talking that quick. So I wanted to start with like the 2.0 version. I think 1.0, I'm kind of assuming that 1.0 is like so old that I don't know if I've ever if I've seen many 1.0 devices at all. So let's look at 2.0. And like the host controller interface is called EHCI, right? Enhanced Host Controller Interface. And it looks like this is some form of like spec that says like, look, we're going to have like a bunch of different hardware vendors make these things. But we don't want to have to write like a new driver for every single one. So let's like make a set of parameters that you can use to talk to this thing, and we'll just all agree to use the same parameters. So what are those? On a PC, you will normally find the EHCI USB controller on the PCI bus. In fact, is the only access method specified in the spec. Great. USB 2.0 supports interfacing with USB 1.0 devices. However, EHCI is not expected to support them. That makes sense. Instead, you will find a UHCI or OHCI companion controller. So you must implement OHCI and UHCI as well. I wonder if that means that like my PCI device will show up at both addresses, because I think I've seen in the OHCI, it's similar. They have like, they will be at this specific class, this like specific ID in PCI space. So it'll be interesting to see if we see when like both EHCI and UHCI/OHCI device IDs as we iterate through. And we will have this specific thing. So I guess the first thing to do is to just like figure out if we have that PCI device. So if I go into like my like PCI device enumeration, right now, how does this shit work? We create a PCI device, and we like have this like find device function that iterates over all of like the entire bus and returns a PCI device. I think this is actually kind of wrong, actually, because how do I say this? If I have lots of PCI devices and lots of drivers, every time we like iterate through one of these, every time we like try to instantiate a driver, we're going to search the whole PCI address space again, which becomes like, it's like backwards, right? It becomes like n square, or instead of like constant time where it's like defined by the number of slots on the bus, it's going to be the number of slots on the bus times however many drivers we're instantiating. So probably we will eventually want to convert this into like an iterator where we iterate over the devices and then dispatch those to their corresponding drivers. So maybe we'll do that now. So I'll just say at like 15:15, we're going to convert PCI device instantiation to iterator. So what are we going to do here? And the reason I want to do this now is because it'll kind of like affect the way that the code is written for like instantiation. Right here, what we do right now is we construct our PCI device and we pass the PCI device handle into this like RTL8139 driver, and then he probably calls find device inside. Yeah. And so what we actually want is we want some sort of like mapping that maps IDs to drivers, and doing that now will fix us from having to like refactor a bunch of drivers later. So it looks like all we have to do for our iterator is jump through each device num and bus num. So I guess we'll make a new thing called like pub struct PCI device iterator. And we'll impl iterator for PCI device iterator. Maybe we'll say iter. I think that like that's a common abbreviation. We probably need to use the iterator trait. Maybe not. Maybe it's like built in. Yeah, it actually looks like it's fine. So the item will be a PCI device. And what are we going to do? We're going to iterate over, we're just going to take this loop and stick it outside. So we have self.bus num is U8, and the device num is also a U8, it looks like, so they go from 0 to 255. So now instead of doing it in nested for loops, we're going to say, first, we're going to get the thing. Oh, this is going to turn a result option, I guess. Or a result PCI device. Or what was the error here? Invalid header error. Okay. Let's see. So he doesn't like. This needs to have the bus number and device number inside. We also need, we are using like functions from the PCI bus, like this like config read thing. So we actually probably need to keep a handle to the PCI device inside, which means that I need to have a lifetime associated with this iterator, which means that here I need to specify that I don't really give a fuck about the lifetime. It can be for all lifetimes. This is a broken case here. And then here we were doing this check for probe vendor and probe device, but we don't have to do that because we're going to return them all. Like, we don't have one that we're like specifically searching for. Here we say that we have the bus number and device number. This now uses PCI config read, which is self.pci. And then after we do all this, we need to say if self.device num is equal to 255, self.bus num plus equals 1. Oh, I guess first we say if device num is 255 and self.bus num is equal to 255. I guess we cancel. So this is kind of interesting. We've put these as like U8s, but the problem here is that like if we can't append like we can't handle without like one extra bit, we can't say that we're done iterating. So we'll just say bool finish. We'll say that like finished iterating is false, a bool that's false. And here we'll just say self.finished iterating is equal to true. And then here we'll say if self-finished iterating will return that we are done. None, baby. Okay, and here we need to take in PCI, and this guy actually has to be mutable. It turns out. So here we pass in the PCI bus when we do our upgrade. Perfect. Perfect, perfect, perfect. I messed up the order of operations here, though. It's lifetime, then mutability. Okay, so now it looks like everything's compiling, and now we just need to make sure that we increment everything. So here we do else if self device num is equal to 255. We set self.device num equal to 0. We've done this set. And self.bus num plus equals 1. And else the normal case is self.device num plus equals 1. Okay. So this should iterate over all devices, and then we can just return ret. And he is actually in the wrong order, so I just take this transpose out. He wants option result, not result option. Okay. So now we have this like device iterator. And then if I remember correctly, when we iterate PCI devices, there's like a special flag for things that don't matter. How do I say this? So, like what we're doing here is we're iterating over all addresses in the PCI space. So every vendor and device number, bus and device number. And when we do that, there's going to be a lot of stuff that isn't plugged in to that specific spot. And so if I remember correctly, there's like a way to detect that. So let's maybe look at like PCI on OSDev Wiki. Look at like vendor. Here. There are 0xFFFF is the non-existent device. So this is vendor is 0xFFFF. So if we say, we'll put this in a loop, I guess. And here we'll just say if probed vendor is equal to 0xFFFF, continue. Except we don't continue, we do this like increment stuff. So maybe we'll just make like a little helper function to do that iteration increment stuff. So we'll say function increment iter is takes in self by reference, mutable reference, and he just does this shit. So if we probe vendors xffff, we say increment iter and continue. Otherwise, we say we go through the rest of the stuff and we say self.increment iter and return ret. Okay. So that should make sure that we only ever return valid devices. And that should work. Okay, so let's make a pub function iter devices, I guess we'll call it, who takes in self-mutable reference because he needs to be able to write to the PCI bus. And he's going to return a PCI device iter. And all we do is we make this guy. Oopsies, what did I just do? Copy this guy. Paste him down here. So this is a PCI device iter that takes in self by mutable reference. Finished iterating is going to be false by default until we get to the very end. The bus number is going to start at 0, and the device number is going to start at 0. Great. PCI device iterator has to be public, which it is, and it has a public iterator implementation. Great. So now I should be able to say for device and PCI.devices. Maybe we'll just like say PCI device, and just see what we get. So what I'm hoping to see here is like some devices made, but we have this device already in use shit. So where does that come from? Why is it saying that? So when we like create a PCI device, we say nobody else can make this device again, which means that we can only call this upgrade function once. And it's just because we're not like correctly freeing the devices at the end, which is kind of annoying. I was kind of hoping I wouldn't have to handle that. I guess for now, let's just remove that check, I guess. Which is annoying, but I don't want to deal with it right now. So we'll just do this. Okay, so we found a bunch of PCI devices, and probably what we want to do is we want to write down what their ID is. So each PCI device, I guess here on our general PCI devices, let's write, let's like make a function to get its vendor ID. So he takes self by reference. He also takes in PCI as a way to like interact with the bus. And what does he return? He returns like two U16s, the vendor and device ID. And does he need to take himself in by mutable reference? I don't know. We're kind of using mute self everywhere. Let's just keep doing that, I guess. And so then we go to our PCI find device. What does he do? He reads this, and this is what he gets back. So he reads self-adder.busnum, I assume is like the name here, bus and slot. So he reads the bus, he reads the slot, he reads this thing, so it's PCI config read bus slot 0, 0, and then he returns vendor and device. We'll call this reg. There we go. And then we turn vendor device. Which means here in our main, we can, as we iterate, we can say let ID is equal to, I guess we have to match it. So we say like match device. And if our device is a general thing, oops, that's wrong. He's a PCI device. General. We say, we got a general PCI device with ID, and then we say device.id, and we pass in mute PCI. Great. He doesn't have this thing PCI device, so we'll just include that. So here we say from IO we have PCI, and here we just include PCI device. And I think that this is good. Mute device, we want to borrow it as mutable. Ref mute device. Cannot borrow device as mutable. Device is not declared as mutable. Do I write mute device here? Cannot borrow PCI device as mutable more than once. Oh, that's fucking annoying. So in order to iterate devices, we need to talk to the bus. But then in order to get the ID, we also have to talk to the bus. So is there a way to get around that? So why config, read, and write are mutable because they do like this like address select followed by a read or write. So it kind of makes sense that these need mutable references. Because otherwise they can't yeah, otherwise they have problems. I see. What does our so probably what we do is we just stash these guys probably. So we say let PCI devices is PCI devices. We like collect all of these into like a vector. So we'll just do this thing. The same thing we did before, except we say this is a vector of PCI devices. Fantastic. We do this match thing. We don't do this info thing. Instead, we just return device. And so I guess this is like filter map instead, and we return some device. This is of type option PCI device, so I just do this, I guess. Some device, like this. What doesn't he like here? This is found to be this, and this guy needs to return none. I see. Wonderful. So now I have these PCI devices in a vector, and then I can iterate over the PCI devices. And now I can say with ID like this, and now I should be able to say PC device ID, and I pass in PCI the bus as a mutable reference. And we'll say we have to get the ID first, or else we have double mutable reference shit, I think. So I think I write it like this. Hey, no more errors. Let's go, baby. So hopefully now if I run this, I should be able to see, hey, there we go. Very cool. So I found all of my PCI devices. And now let's see, we should see like the network card that we were using before. He was looking for a very specific device. And so we've written these in hex, and so let's maybe format these in hex. So we'll do like this. We'll write some hex numbers, and we'll say id.0, id.1. So now when I run release, let's see if we see something that resembles our network card. So what was our network card? RTL 8139. 10EC 8139. 10EC 8139. So we do find our network card, which is great. And now, can we find, do we also see our EHCI controller? Because that was the reason that we did all of this, is because we want to be able to map multiple devices. Fuck. So we also have to look at the class ID, subclass ID, and interface value. So what are those? What are those? So we have device ID, vendor ID, class, subclass. Class, subclass, interface. So we have class, subclass here. Where is the interface ID? Ah, probably this guy, the prog interface. So probably we need to read bytes. What is this? We read register 2 with offset 8, and then we pull out the class, subclass, and interface versions. Let's take a look at that. So in our PCI shit, where we were pulling out ID, where the fuck was that? Here, what do we name this now? I guess ID is still sane, and what are we also? We are also adding this like class, subclass, program revision ID, which is like what do I group those names together as? There's no like sane word for that. Is there? Class? Interface? Interface seems reasonable. We'll call it that for now. We'll say interface ID. And he does the same shit, but now he returns. We should probably name this. So we'll say struct PCI interface ID. And he has a class code, which is a 8 bits. Subclass code is also 8 bits. Interface code U8. I don't like having code everywhere here, so I'm just gonna write this. And I think I'm used to having to write class with a K because class is usually a reserved keyword in like Python and C++ and shit. But I think in Rust is actually not. So it's pretty funny that my default was to just misspell it, but I think this is fine. And fuck it, we'll put the revision in here too. We will make this a debug struct so I can print it easily. And then here we'll just say PCI interface ID. Great. So now all we have to do is we need to query this register, which is register 2. And so what is like the interface of this? Function and offset. Bus slot function offset. What the fuck? Where offsets seem to be 4-byte aligned. So presumably the offset is what I care about. Probably. Yeah, offset 0x8. That seems reasonable. So here I just write 8. Cool. So now I just pull out the different components. So we'll return a PCI interface ID, and his class code is the bits 24 to 31. So we'll say reg get bits. We are shifted by 24 when we're doing 8 bits. So then we have subclass, interface, and revision. And we're just going off by 16 on each of these. I wrote interrace instead of interface. That's really bad. Bad typo. And here we need to cast all these to U8s after. Great. Great. And so now probably in main, I should be able to say interface ID is equal to device interface ID. We pass in the PCI bus. And then we just say and interface like this. And I misspelled interface wrong again. Interface. Okay. He doesn't like that's a private type, so we just need to put a little pubaroo on there. And probably all of these guys in public as well. Okay. So, oh, there's this annoying shit where if my lines are too long, I don't know who's doing this, but someone's chopping this shit off, and that bothers me. If I put it into less, can I scroll right? I can, but how do I get back? Okay, whatever. Oh, here we go. Okay. Maybe it's like a tmux config that's not wrapping correctly or something. But whatever. So here we're looking for, in our EHCI, we're looking for these guys. They're hex formatted. Ugh, that's annoying. So this is C is 10, 11, 12. This is 3, and this is gonna be 32, I think. So here we see 32. Here we're looking for class ID of 10, 11, 12. So we don't see any classes bigger than 6, which probably means that we don't have a USB controller passed in. So maybe let's say we're looking right now for USB controller, and we'll just say a little late here. And so I guess let's try to like look for QEMU command line arguments that we can use to initiate instantiate a USB host controller. QEMU USB. I see. So I just throw in a device QEMU XHCI. That seems easy. So I say here, device QEMU XHCI. And so hopefully now I see it. Ah, yeah. Look at all those 12s. Now, should I be concerned that there are so many? Right? Like, why is this? Am I like the fact that I'm seeing this repeat over and over again makes me think that I might have a bug with my register selection, right? When I'm enumerating my bus, PCI bus and slot, I'm assuming that there's actually only 4 things plugged in here, and I'm just really fucking it up. Hello, what's up? So probably when I'm entering devices, the big thing here is for each device, I'm pretty confident that my bus number and device number are incrementing correctly because we're seeing evidence of that here, right? We're seeing bus and slot increment linearly. I wonder if there's some pattern here where we're seeing 0, 2, 4, 2, 4, 6, 4, 6, 8. So maybe I'm writing the when I'm selecting which device I'm reading, I wonder if I'm doing it wrong. So select PCI address. Is this just implemented wrong? Bus slot func offset. So we set the function. This would, I guess the problem here would be related to bus and slot. So if my slot is off by 1 bit, that could be causing this. If I'm seeing repeats, I'm pretty sure that if I'm off by 1, does that make sense? It might. I don't know. Let's see. PCI. So when I select an address, what am I supposed to do here? Command register, status register. Where is it even going? This is going to address. PCI config offsets. This is going to the first byte of PCI address space. So there were 2 address mechanisms. I'm probably using this one. This looks right. So here I'm using 0 to 7 is the register, 8 to 10 is the function number. So 8. This should be 3 bits for the function number. the device number should be bits 11 to 15, which is 11, 12, 13, 14, 15. That's 5. And bits 8, 9, 10, that's 3. 0, 1, 2, 3, 4, 5, 6, 7, that's 8. So we should see 8 bits here, 3 bits here for the function number, 5 bits for the device number. 16 to 23 is 8, I think. 16, 17, 18, 19, 20, 21, 22, 23. Yep. And then 24 to 30 is reserved. So I guess probably there might be something wrong there, but let's leave that for now. And then bit 31 is enable. So that should be right. I wonder if the function number being wrong was like fucking me in some way. I don't see why it would, but I don't expect this to be fixed. I still am seeing repeats, and I'm seeing repeats every 32, which is like a pretty good indication of something being wrong. Hey guy, what distro do you have? Are you talking about what distro am I making? I'm not really making a distro, I'm just making some random OS. But if you're talking about what distro am I running on, I'm running on this thing called Nix OS, which is like, I don't know, in my mind, like kind of like a meme. It's pretty sick, but I would never recommend it to someone. Its whole thing is like, if you've ever used infrastructure as, what do they call it? Like Terraform for AWS? Like, what is it? Not Terraform. Yeah, Terraform. Terraform library. What do they call this thing? Anyways, there's like this like concept of being like, I want to define my whole infrastructure in like a config, and that way I can like bring it up consistently on like multiple devices, whatever. So NixOS is like that for operating systems, where like you specify like your whole operating system in like a config file, and it builds the whole OS for you. And so when you like upgrade your packages, you go like, I would like to rebuild my OS, please, from this config with the latest and greatest packages. And I don't know, I like the idea of like the consistency and being able to like track my operating system in a Git repo and stuff. It's pretty fun. Anyways, that's what I'm using. I would never recommend it, but if you like it, it's one of those things where it's like, if you wanted it, you probably would seek it out. Is kind of how what I would think about it. Okay, so this is repeating every 32, which means that it feels like a power of 2 problem, which means that I could be off by the wrong amount. I think just changing numbers randomly is a bad way to fix this. So, where am I going wrong? 32 bits. It seems like I feel like I've gotten this right. Bus, slot, func, offset. And the enable bit. They write the address, and they read the word back. Okay. So why the fuck am I repeating? Why the fuck? I guess maybe here we should double check that, oh, hold on. My device number it can only be 5 bits. There are only 32 options. So this is it's just my loop is just iterating over the wrong number. This should be 32. And can my bus number be 8? My bus number is 8 bits, but this is only 5 bits. So that explains it. There was nothing wrong other than I was just iterating too many devices. There we go. Okay, so now I'm only seeing each PCI ID once, and I should have found this PCI, or this like XHCI host controller. Pretty cool. Pretty cool. So now I guess what do I have to do is I have to dispatch this like PCI device to a driver that will handle XHCI shit. Cool. Cool. So what does that look like? We're going to iterate over all devices. And we're gonna do like some things here. Like we're gonna say we're gonna say like match ID. Probably. And I guess we're gonna say like our network card driver. Let's call this. We'll say that we're gonna do like driver dispatch here. So like 5030, we're gonna do driver dispatch. PCI driver dispatch. So he's going to say like device PCI ID. He's going to have like an associated constant with him, I guess. And if we see the PCI ID of the RTL 8139, we're going to construct him. So I guess we say RTL 8139 is equal to this. Is that reasonable? And then up here, we just say like, let mute RTL 8139 is equal to none. And here we throw a little sum around this guy. Cool. And then here we say RTL8139.expect failed to find PCI device ID for RTL8139. Wonderful. And so now all we have to do is like define the PCI ID. So here when we call find device, we'll just say RTL8139, he's just going to say const PCI ID is equal to this. And I guess this is a U16 pair. And we'll make it public. And when we construct him now, instead of passing in PCI and finding the device, we'll pass in the device directly. Which is a generic PCI device, I think. Nice. Nice, 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 nice. Okay. So all of this goes away. And everywhere where I wrote RTL device, I just replaced that with device here. And this guy needs to be taken in by mutable. He needs to say he's mutable. Great. I think this all compiles. And now all we need to do is propagate some of that stuff. So this guy comes in here. Right, we're passing in the device externally now. Great. And in main, when we construct this guy now, we pass in the device. Who... I guess we need to construct this down here. Okay, so now we have like this way to like iterate the devices, which means in our PCI, we can probably delete this find device function. And if we run this, we should find that like our network stack still works. So if I go here and I just like go here, we are seeing like network stack doing something. We're seeing like our web page open up. So that means that our driver is constructing sanely, which means everyone's happy. Very cool. Very cool. Okay. So I think I saw some complaints about unused shit. So in the RTL8139 driver, we have some like unused failure types now. So we'll just delete those. Because before those failures were like, hey, I'm trying to like parse this PCI device, and it's not what I expect. But now we can't get into that state without it being correct. So hooray for us. Hooray for us. Target check. Okay. And so probably here we can add, we'll cargo format, we'll lint, we'll make sure that all of our, like, everything's still passing. Cool. Let me just double check something. Oops. We're kind of like in the wrong spot, but that's okay. We'll fix that in a second. So I think we can add everything except for the USB stuff, where we added the XHCI device. And then we are good to make a quick commit. All of this stuff is stuff that I wanted. And then the only thing that I made a mistake about there was somewhere we commented out this. And I just want that to come back in. So that was like a quick sanity check. I think that it should be safe to run with that now. And so we'll just do a quick run release again. So we just want to make sure that we're only iterating devices once, essentially. And it looks like we're good. There's no panic. So I think we're good to say, we'll make a commit that says, change PCI device instantiation order. Instantiation order. And we'll say, previously, we were iterating the bus for every PCI device. Iterating, I guess we should say, all of PCI bus space for every PCI device to find the specified ID. If we have more than one PCI driver, one PCI device driver, this does not make sense. Instead, we should make a we should iterate the PCI bus space once and construct the driver we care about based for each ID. Okay. And now, let's just stash really quick the rest of our stuff, and let's make sure that we're in the right spot. So I just want it to be here. So I'll just say git rebase back from one commit back onto this guy. And now I'm in the right spot where hopefully my unit test will run when I run the lint script. Great, my unit test passed, so I know I didn't like really fuck anything up. I don't like this like info log being there for each device that we find in PCI device space, so we'll just delete that log. We don't actually need it. Or maybe we'll change this to a debug log, which means it won't show, but it'll be there for if we need it later. Cool. And we'll just amend that commit real quick. Otherwise, it looks good, and then we re-enable the QEMU wrapper change that adds the XHCI thing, and we can use that. Or sorry, EHCI, not XHCI. Oh shit. XHCI is wrong. That's USB 3. I want EHCI, baby. Does that? QEMU EHCI is not a valid device model. Well, that's fucking annoying. Sorry, let's put this back to info log. I want to see what we're looking at again. And we'll change this back to XHCI. And let's see what we get. So here we have class ID 12, subclass 3, interface 48. And we wanted interface 20. So can we do like... Oh, here we go. EHCI controller support. The QEMU EHCI adapter supports USB 2.0 devices. It can be used either standalone or in companion or with companion controllers for USB 1.1 devices. The common controller setup is more convenient to use because it provides a single USB bus supporting both USB 2.0 and 1.0 devices. 1.1 devices. See next section for details. When running EHCI in standalone mode, you can add UHCI or OHCI controllers for USB 1.1 devices too. Each controller creates its own bus though, so there are two completely separate USB buses, one for 1.1 and one for 2.0. Devices must be attached in the correct order manually. The easiest way to add a UHCI controller to a PC machine is with the USB switch. QEMU will create the UHCI controller as a function of the PIX 3 chipset. The 1.1 bus will carry the name USB bus 0. Okay. You can use a standard device switch to add an EHCI controller to your virtual machine. It is strongly recommended to specify an ID for the controller so that USB 2.0 gets an individual name. For example, this. This will give you a 2.0 bus named EHCI.0. I wonder where these names come from. I guess we'll figure that out later. When adding a USB device using the device leg, you can specify the bus that should be attached to. Here's a complete example. And then we just yoinkies this whole thing. How come when I hit Control C, the tab bar on the left is scrolling? What the fuck? That's so weird. I don't think I've ever seen that. And it's only if I press Control C in combination. If I press C, nothing moves, and if I press Control, nothing moves. So it's just Control C to get. What the fuck? All right. Oh, it happens if I right click copy too. That's so weird. What a weird bug. How strange. I hate software, man. Okay. Okay, so let's take a look at this. So I don't really care about this like USB storage. Keeping the USB tablet in there is kind of nice. So let's do that. And then there's like all this like extra shit in here. Oh my god. Okay, USB. This is a device. And then that's a device. Okay, so the USB tablet will probably be my mouse. I'm pretty sure that like in the QEMU world, your pointer like hovers over the space and they just consider that you like tapping it in that exact location. I don't know. I think there's a reason why that's like a nicer way to do it. So if I cargo run now, do I see my EHCI host controller? Class 12, subclass 3, interface 32. Which is an interface value of 0x20. 0x20 is 32, I'm pretty sure, because 10 is 16, so multiply that. 2 is 32. Boom. Very cool. Very cool. So, it looks like we've found the controller. Very cool. Which means that we can start probing EHCI host controller device. Or maybe we'll say like right start EHCI driver. Very, very cool. Ugh. Okay, take a sip of coffee. Wake me up a little bit. And let's just start banging out a driver, and then we can start like probing what we see from it. So we'll just make like an EHCI driver module. I've just been throwing everything at the top level. Eventually I'll have to fix that, but for now, we'll do it like this. Struct EHCI. And when we construct him, maybe we won't like make a new thing right now. Maybe we'll just make a free function that we can just start poking with. So we'll call this what, like EHCI probe, and we're gonna take in our device is a PCI device, and we're gonna need to take in like the PCI subsystem. And I guess we don't really have any idea what else we'll need. So we're going to use our crate PCI IO, PCI, and PCI device. Great. And then here, when we iterate our PCI devices, we're going to say if, else if. So the first thing we do is we check if it's a network card with a specific vendor ID. Otherwise, we check if the interface ID class is equal to 0xOC and the interface ID. So after supporting USB is the mouse support. Yeah, but I suspect that mouse support's going to take a while. The end goal, I don't know if you were here at the beginning of the stream. Probably not, because why would you be? The goal here is I eventually want to get to the point where I can run Doom, because this guy on YouTube said, can it run Doom? And I'm like, fuck, it can't. So I need to make USB support so that I can add mouse support so that I can move the cursor around. That's the goal. So the subclass is going to be 0x03, and the interface value has to be 20. So interface ID interface version is equal to 0x20. So in this case, we are pretty confident that this is an EHCI device, and so we say EHCI is equal to, I guess we'll just EHCI probe. And we'll pass in the device as well as the PCI subsystem. And this comes from the EHCI module. And this doesn't take in a PCI device. This takes in a general PCI device. Cool. Is this just for wasting time, or do you want to make it usable? Well, waste might be a strong word. I think in reality, no one who makes an operating system is ever gonna have it like be used for anything interesting, right? Like nobody's ever gonna replace Linux, Windows, Mac, BSD, right? But kind of like the goal I think here is like, if I implement enough of an operating system for it to be usable, I should end up with like a pretty good understanding of what's happening under the hood. And that's really mostly what I care about, right? It's like a learning experience. So, right, like if I'm in normal Linux land and I call like socket create with sock dgram, and then I send socket, like I send a message over TCP, or like I create like an HTTP server, like it would be not, I want to have like a good intuition of what's happening everywhere. And like right now I have like a pretty good intuition on some parts and not on others. So if I make an OS where I can open, like I have an HTTP server, now I know what pieces need, like what's going on there, right? Which long term maybe lets me make better guesses, but it improves my intuition when I'm working with bugs and trying to guess what performance would be, etc., etc. That's a goal. It's also good content, right? I think it's fun to watch OS dev. And it's like, there's an infinite hole of stuff to explore, which is also fun. All right. So let's look at this EHCI host controller. Let's see if we can like glean any information from it. So what does it have? It has these capability registers, has operation registers. So these are like capability registers, I would guess, just by the name, are probably read-only, right? I can probably look at each register, and I would imagine that I shouldn't be able to write capabilities because the card probably only supports some amount of things. This says some stuff. I don't know what any of this means. So probably I'll just ignore it, because if I can't understand what any of the capabilities are, then why the fuck would I read them? Ignorance is bliss. But it does seem like I need this capability register length in order to get to the juicy stuff over here, which is like commands. How much time do you think you've invested in this huge project? A very rough approximation, of course. So I've been working on this like maybe almost daily-ish since like, well, daily is wrong. Maybe like 5 days a week on average, plus some off of, I think I've actually probably made a little bit of progress at least every day since the end of August, beginning of September. So maybe 2 hours times 30 days a month times 2 months. So like 120 hours-ish, rough approximation. Yeah, that is not that much, and it turns out you can get a lot done if all you're doing is sitting down and focusing on it, right? Like obviously there's like extra stuff going on, how do I say this, right? Like, you know, I might like wake up and think about it, right? Because like it just happened to be what's on my mind. So that's like, I'm only really counting like active time. But yeah, if you're curious, all of this, like all of the progress has been documented on YouTube. So there's a YouTube just like linked in my Twitch description, and if you want to go back and watch any videos, you can like see the implementation of any feature, which is pretty fun. There's also like the GitHub has everything broken down commit by commit. So if you want to go through and like see something in particular, you can go back and is there anything like generally the commit messages should be pretty good. Right, so I've tried to describe why I've done everything I've done. So if you want to go like browse through the GitHub repo, that's a good way as well if you want to catch up. Okay, EHCI. Let's see. So we have these capabilities. I don't know what any of them mean. We skip those for now. We jump over the capability register length in order to start looking at the operation registers. And I guess what would be nice is if we could I guess the first thing that we probably want to do is like enumerate the devices, see if we can like fucking find anything on our USB bus. Because like presumably we should have that USB tablet plugged in that we asked QEMU for. And I think I saw somewhere in here like a device enumeration section. So they have basic concepts and nomenclature. Boring, but I'm sure that we'll need them. So they're talking about, I've skimmed this a little bit. Basically, they have like functions, interconnections, hosts, and hubs. They have this like little diagram here where they say you are a computer and you are the root hub or the USB host. They have functions colored in blue, where function is just like a funny name for device, right? They have like a scanner, a router, speakers. Who has USB speakers? That's crazy. I guess, why not? Camera, phone, whatever. These guys go through hubs. And then this is kind of funny. I've never seen this in a diagram before, where they color code functions as blue and hubs as red, and then they just put a purple thing in here with no label. I think that's like pretty funny, because they're like, obviously red and blue make purple. Keep up, idiots. This took me so long to figure out what the fuck this was. But I like it. That's pretty funny. Okay, so what do we have on here? So we have functions, we have hubs. The communication flow. Figure 9 illustrates the concepts of USB communication. Okay, so I am the host over here. That's me. On my host, there is software. What a funny blob to put in here. It's like, what else would I be running? Yeah, sure. I guess I have software, and in my software there are buffers, and each buffer is connected through a pipe to a USB logical device endpoint. So I think that what I read somewhere, let's see. Let's find that diagram. Here we go. So within a device, I read that there is a configuration attached to each device. So maybe I could put my device into like separate modes, I think. I'm not really sure. But like configuration kind of implies that, right? Especially if configurations have interfaces on them and each interface has an endpoint. So I presume that like interface has like a collection of endpoints, maybe because there's like multiple things that you could do with a device, right? If you have like say I have like a keyboard over here. Hold on. This guy is both like a keyboard and a mouse, right? He's got a little trackpad on him. And you can see when I wiggle it, the mouse moves around. Right? So like I'm kind of guessing that like if you were to model this like keyboard mouse combo as like one device, which it is, right? It's literally one thing. You could say that like you have an interface on there that's like keyboard, and you could have another interface on there that's mouse, right? You could have both of those things like within one config. I would guess maybe this thing is actually implemented as a USB hub. That wouldn't surprise me either if like this thing is shown as like, I wonder if I can like actually look. I'm not going to install it. I give up. That was quick. But like you could implement that as like a mouse and a keyboard like stuck behind a hub together, but you could implement it maybe as like these like multiple interfaces. That's my guess. And maybe on each interface you might want to do multiple things. Like you might have one endpoint for like I'm wiggling my mouse around, and another one for like I clicked a button on my mouse. Again, I'm just guessing, but like that would make sense to me. And so what they're saying in whatever fucking picture I had open somewhere, this guy, they're saying that like I have like a ring, like a buffer for each endpoint that I'm talking to. And so that makes sense, right? If if both of these things are like creating events, you could like imagine a system where you have like a circular buffer, and like when I click the mouse, like the mouse click events ends up in this like queue that I have to service or something. Who knows, right? Someone does, I don't. I'm just guessing. I feel like a strong need to reiterate, I haven't really done much reading. Okay, so they're saying, yeah, you have buffers associated with each endpoint, essentially. And these pipes, probably, I probably put something in the buffer queue, and then I go like, hey, device controller, could you send this buffer over to this guy at this endpoint? And he goes like, okay, sure, I will. I'll set all the bits to do the right thing. That's my guess. And so every endpoint has like metadata associated with it. So they're like, hey, you can only give me like a thing that's this big because like my endpoint on my device only has like 16K allocated to receive shit. So don't send me something that's 18K, where 18K is probably like actually like a fuck ton of data to send to a mouse or something. But anyways, not important. Beside the point, right? Error handling requirements, bandwidth requirements, frequency, latency requirements, blah, 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 blah. Nothing about this is actually like, how do I talk to it? So I don't really care yet. I'm sure that this will come up later. As an example, an all-in-one printer scanner device may implement an endpoint number for printing functionality and a separate endpoint number for scanning functionality. So that's actually like very close to what I guessed, when I could have just read 3 sentences further. This will happen a lot. I prefer to guess and check versus actually read, which slows me down sometimes, it speeds me up other times. Endpoints have a specific direction. 2 endpoints may have the same endpoint number. Okay. So there's like one in and one out, but opposing data transfer directions. All functions implement 2 such endpoints and the endpoint number 0. With the endpoint number 0. Only endpoints with the endpoint number 0 may be accessed as soon as the device is powered and has received a bus reset. So I don't know if I have to manually set a device reset, but presumably I can probably just read endpoint 0 and get some interesting data out of it. All USB devices implement input and output endpoints with an endpoint number of 0. Cool. These endpoints are collectively known as default control point. Cool. Endpoints with an endpoint number 0 are special in that they are accessible whenever the device is attached, powered, and ready to receive a bus reset. In the interest of backwards compatibility, all high-speed functions must support these endpoints even when connected to the hub at full speed. This means that high-speed devices must be able to reset at full speed as well as respond successfully to standard. Okay, sure, whatever. Whatever. So endpoint 0, always valid. Probably has some like interesting shit in there. Did it say that like the interface of 0 is well defined? Default control point are special in that they're accessible. It doesn't seem like I see anything about like a predefined interface for 0. Default control pipe is a special type of message pipe that is always accessible. Information required to completely identify a device associated with the default control point. Okay. So basics. Oh, well, I guess we should read this pipe shit while we're here. So he associates software on the host, a buffer on the host with an endpoint of the device. There are 2 kinds of pipe. There's streams, no structure on the data being transferred. So probably like if you have like a USB stick, you would use this. Message pipes impose some sort of structure. So this is like this probably sounds more like what my mouse is going to look like. Stream pipes are unidirectional. Message pipes are multidirectional. Sure. Pipes have the following attributes. Whatever. Data flow in a pipe is independent of data flow in any other pipe. Most pipes are available after the device has been configured. Yeah, okay. Nothing too crazy there. Nothing too crazy. So what's going on? USB transfers. So a token packet indicates the type and direction of the transaction, the device address, and an endpoint number. I see. So probably I'm just going to get token packets, probably, because like on my end as the host, I can't make token packets because I don't know what the device is yet. Maybe I could. If you could maybe like get a device and say like, hey, you're this now. But it seems more likely that like my mouse will be plugged in and he'll be like, hey, I'm a mouse. What's up, dude? And I'm over here. Come talk to me. Just a guess. Depending on the direction of the transaction, either the host or the function needs to send a data packet, which may be empty, but whatever. The receiving device responds with a handshake packet. So this is like reminds me of like TCP negotiation. There's like this like 3-way handshake where I go like, hey, I'm over here, and I go, and here's some stuff, and I go like, oh yeah, I got the stuff, I'm over here, don't worry, you can talk to me, send me your shit. There are 4 types of data transfer take place via pipes. boring. Control transfer, bulk data, interrupt data. Yeah, okay. So that's whoa, that's way down the line. Right now, I just want to like find the fucking thing. So if I can find a token packet, I'll be very happy for now. Then there's all this stuff about like different types of transfers and failure types and all that shit. Advanced USB concepts. I'm just gonna skip that whole section, right? Because I'm far from being advanced. I don't know if I need to understand the protocol, right? It really depends on if the like what level the host controller is at. Like, do I need to know that like do I need to send this sync? I guess I could read a little bit of this section and find out. Right? We could always do a little bit of reading. So we transfer packets, which is just a bundle of data, which is has a header and some errors and some data, whatever. Sync field is omitted from packet diagrams, and usually other material meant for programmers. I guess because this is probably like on-wire shit that like we don't really care about. Because USB sources often reference sync field, and that may confuse us. But for clarity, the system programmer does not need to know about the sync field. All USB target packets start with sync field, which serves, unsurprisingly, as a synchronization method between the receiver and sender. Okay, so we can probably just assume that this is like in the same way that like I think I saw this same concept on Serial, where you have like, is USB like 2-wire protocol? What is, like, I think it's 4-wire. Yeah, 2 are used for charging, 2 wires are used for data transfer. So I think it's just like RX, TX, and like power. And so presumably you just have like this like read section, and he goes like, there's nothing happening, and then he goes like, boop, 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 boop. Here is my like magic back and forth signal. Just be like, hey, this is like the start of a packet. And then he sends like his like actual data, which like, you know, has like mixed highs and lows, whatever, like doesn't matter. But I think that I've like, they're just saying like, yo, USB physical device, you could just like match this pattern, and when you see that pattern, then you'll know that like we're at the start of a thing. And then probably if you like send this inside the packet, I would presume that there's some sort of way of flagging that that's not actually a thing. Like you might have to like put some gaps in between or something. Just a guess, but sync field consists of 6 or 30 alternating bits for low and full speed, high speed buses. Okay, I was gonna say like 6 or 30. That's so fucking weird, but it makes sense that for high speed buses you would need more. Because there's just like a greater chance of collision, probably. I don't know. Last bits or the sync field are high and low. High speed hubs may drop up to 4 bits of the sync field, so high receiving device may not see the entire field. Yeah, makes sense. Okay, so then after we sync, we get the packet identifier. There are 17 defined PIDs. It's 8 bits wide, and the 4 bits are simply a component of the first 4 bits. And that makes sense because you might want to do some like this, like a very naive checksum. When you would probably just like fucking discard the whole packet if you don't see something that makes sense. PIDs are categorized into 4 groups. Oh, I see. So this is how we know what type of data we're receiving. So we're looking for PID token at first. Then there's address fields. So where does this come from? So we see the PID and the address field specify a specific endpoint. So how do I know where this address field's coming in? Oh, I see. It's if you see these PIDs, then there's an address field. Okay. But like this is like so far past what I'm looking for, because like I don't even know how to like talk to a device yet. Like, how do I say this? I don't care about what the data is if I can't even see the data yet, right? And that's kind of like the level I'm at. So here we go. USB transfers revisited. So maybe they're saying like, now that you know what the data is, here's how to send it. Maybe. So they've given us a lot of info. It's easy to get lost in details. Blah blah blah. With blah blah, nothing in here looks too exciting. I just want to see like a control flow diagram or something. Like, how do I like just give me the sequence of operations? Setup stage is simply if it's setup transaction. So how the fuck do I like get into setup? Oh, here we go. Okay. Oh, okay. This looks interesting. USB device states. So after I plug it in, it's attached. Powered means that someone has given it power. I'm assuming that power is given automatically, right? I don't think that my like kernel driver needs to define the power output to a device, because I assume like it should just always be like 5 volts, I think. Oh shit, maybe I have seen that like high power, like you might like lower to 3 volts if you want to be in high speed mode. Where have I seen that? So I think when I worked on I used to work on like firmware on Linux based like devices, and if I remember correctly, I think it was USB. When you flip into high speed mode, like sometimes you'll go from like 5 volts to 3 volts because it's faster, like physically faster to change the voltage from one to the other. So maybe there's a reason why you would want to do power negotiation in like the USB driver. I don't remember if that was on Ethernet, USB, or something else completely, but I have seen that before at least. So default is a device in the powered state after it's got a bus reset. In this state, the device is accessible at the default reserved address of 0. At this, oh, okay. The host is expected to allow 10 milliseconds before expecting the device to respond to data transfer set reset. So then there's the address state, where a device enters a state after the host assigns it an address. Okay. So this is starting to like come together in my head. So I plug a device in. He says, I'm at address 0. And I go, no. I don't want you to be at address 0. You go to address 55, please. And then he probably writes down in his head, he goes like, okay, I'm 55 now. So forget that 0 shit. Anybody who says 0, that's not for me. 55, though, that's definitely for me. Probably. Now, I don't know how that's going to work on startup, right? Like, if I boot up my computer and there's like 8 devices plugged in, wouldn't they all be sitting at 0? Maybe the USB controller inside itself, like, only powers on one device at a time and waits for the like my software to assign the devices. It could snoop the line, right? It could be like, oh, I'm going to put this. He could be like, okay, I've instantiated one device. And now I'm going to like hold off on all the other ones until you assign a device. And he goes like, oh, device assigned back. That means that I'm good to go again. And like, let's turn on the next one and the next one and the next one. That would make sense, but we'll see. We will see as we go farther down the rabbit hole. Configured is a device state after the host examines the possible configurations and selects one. Okay, and suspended is after a certain amount of time, the device goes like, oh, it's nap time. Makes sense. So USB device enumeration. This is what I was getting excited for. The following describes the process of bus enumeration, which happens after a device is connected to a powered port. Cool. So we can probably assume in my VM that like we have a device connected to a powered port. So we have a status change pipe that comes from the hub, but we have no hubs right now. I hope. I'm hoping to just like dodge that complexity for now and just hope that we have like USB device plugged directly into USB subsystem. The host queries more information from the hub. The host must wait at least 100 milliseconds, so then the hub does some reset processing. Then the host assigns the device a unique address. So, but like then how the fuck do we get the hub? Like you're totally skipping the most important part, which is like, where do I start? I just want to know where to start, man. All right. Then we like read config, blah, blah, blah. So USB device requests. So I think, is this the first thing that happens? The newly this makes sense, right? If we're saying that like when it gets into the address state, he might say like, hey, I'm a device, could you please give me an address? Standard class-specific and vendor-specific requests are made to the USB device over the default control pipe. The setup transaction always has a data payload of 8 bytes, as quoted in the maximum data payload size section of the control transfers. Okay. So I guess we could argue that like maybe that means that when we plug something in, he's going to request a device, because I think that where was that setup shit? Communication flow. Yeah, so where did I see like setup? Maybe it was over here. Handshakes. Yeah, this is what I'm looking for. No, that's not. Somewhere I saw like that like token handshake shit. Handshake. Token, yeah, basics of USB transfers. So, oh, there's also like the default control pipe once a device is powered. So I think we saw somewhere that there will be a device at device 0. And we also like could guess that there might be like a setup packet or like a device identifier packet that comes in. So if we look at EHCI, is there like a thing that we could maybe just read? USB status register. Is there anything here that says like, hey, there's data? Frame index, maybe? Maybe this is like the read head. Asynchronous queue list is a ring of queue head records that point to the next queue head in the ring. Well, I guess, okay, so when we were looking at this, presumably somewhere we need to set these buffers, right? Somewhere we're going to have in memory places for the like physical memory probably mapped into PCI space or something. I'm not really sure how it works. I think the PCI, if I remember correctly, the PCI bus has direct access to physical memory. And so probably somewhere I say, hey, USB controller, here is some memory for you to use. Or the USB controller says, hey, like, fuck off, just don't use this memory. Like, if your allocator allocates this shit, we're gonna break, bro, is like maybe what he says. I don't know. So if I like read through this EHCI stuff, there must be somewhere for me to set those buffers. There has to be. And I guess that those are like per device. So, or maybe it's just like when I send something. No, there has to be a receive buffer. There has to be. Okay. So an asynchronous queue list is a ring of queue head records that point to the next queue head in the ring, and the first transmit descriptor in the queue. As long as the asynchronous schedule flags in the command register, the EHCI controller will start with the first queue head located at the address, the next asynchronous list address register, and process all queue heads until it encounters a queue head with the reclaim flag set. I see. So I guess what happens is I make like a linked list. I go, and in here I'll be like, hey, here is this guy points to this guy, this guy points to this guy, this guy points to this guy, and I like pre-allocate these, and each one of these has like, I'm ready, or like they might have like, I am busy, I have data, no writing to me, please. And probably what happens is like I feed this guy to the USB controller. He like walks this list until he finds a happy face. He puts the data in and sets it to a frowny face. Right? He goes like, oh, you are no longer ready to be written to. You're busy. Then my software like does some processing of this probably. And when he's done, he frees him. So he goes like, oh yeah, I've like looked at this. I know what I need to do. And so like we're good to be written to now. It looks like. And so this gets written to the next asynchronous list address. Where the fuck is that? Next async. So this is in the operation registers. There's just like a register that I can write to. What's the frame list? Oi, oi, oi. Do I actually have to read the spec? Man, imagine actually having to read to do software development. Unbelievable. So they're like data structures, operational. Okay. Host controller initialization. Okay, wow, this spec is already looking sick. Oh, I guess before I get into this though, I did want to see if the 1.0 versions were like easier to understand. And it looks like no. It looks like the OS Dev Wiki is it's trying to be like a little bit of a reference for when you already understand it. You're like, oh yeah, these are the registers. But if I want to know what the registers do, probably just reading the spec for real is what I'm supposed to do. All right, so host controller initialization. When the system boots, the host controller is enumerated. Assigned a base address for the register space, and the BIOS sets the flag. What a funny word. Flag register. It sounds like something really gross. Like, ew, don't look at my flag. Gross. So he sets it to a system specific value. After the initial power on or hardware reset, all of the operational registers will be their default values. Okay, so I guess what we could do, the first thing that we could do is we could just look for this, right? We could make sure that we can like read these values, and if we see this pattern, that we know that we've at least got a handle to the device. So let's do that. Somewhere in here we did a bunch of reading. And now we're going to say we want to prove, this is at around like 136 in, we want to prove that we have found the memory mapped registers. So what we want to do is we want to look at the device. And if I remember correctly, we already have a way to do this. So do what, you might ask? Yeah, I didn't say that yet. Okay, so PCI. They have a bunch of metadata in this like control structure. So if I remember correctly, kind of going off the top of my head here, there's like me, the CPU, and then there's this like these are like memory lines that go to like RAM. And they also go to like IO. And these are like the same lines. So like you have like IO addresses that might go to like the PCI controller. Or like the, like what else? Like serial. And because these are using like the same lines as memory, I can only access stuff in IO by like completely disabling RAM access, which is like makes all other accesses to memory slow as shit. Because like you can't do them in parallel. Maybe I'm kind of assuming actually you could argue that like if you were doing this all on one CPU, everything should be going in order anyways. But like you could imagine that if you have like memory prefetching and pipelining and stuff, like maybe like these things would interfere with each other. I would just assume that, right? Especially because memory mapped IO has become like more used. So you're actually gonna have like you actually have like memory controller. CONT. And like these guys get like mapped directly in here. I assume that that's why this module exists. Anyways, so I have this like PCI controller mapped to IO. And this PCI controller talks to each PCI device. Dev 1. And dev 2. And like there are just like specific reads you can do in here. And one of the things that you can do is be like, oh, device 1 is actually like also directly connected to this memory bus. And so one of the things you can ask is like, where are you connected, bro? Like, can you please tell me what address to access you at? I don't really know how those addresses get like assigned. Maybe this like controller goes through and he like asks each device like, hey, how much do you need? Like, oh, okay, I've got some look at my list, and I was like, oh, at like 40, I could give you 40. You get 40 now. Maybe, I don't really know, I'm just guessing. So what I want to do now is I want to ask this guy where the like memory for my USB device is. And if we can find this list of numbers on initialization, then that means that we've like correctly identified the region of memory that is mapped to the USB device. So if I remember correctly, in the general PCI device, there are these like things called like base address registers. And this should be where the this should tell me where to write to. So I can say find oops, what the fuck did I just do? I already actually have this function, find mmap range, which is like, tell me where the memory is. So here I can just say device find mmap range, and we pass in PCI. And let's just print out. So we'll say that EHCI mmap range is range. Okay. So let's see what we get. Let's see what we get. So here we're saying that we have some memory at this address with this length. Cool. And so what I think we saw in the EHCI thing is that the first thing that we see is the capability register length. So here I should say let cap length is the range. What is like the units of this guy? So here we'll just say failed to find a map range if we didn't find it. And then we say range dot start is the beginning. And this is a, does it say how many bytes this is? Given that this offset goes from 0 to 1, I think we can assume that this is a single byte. So we'll say read volatile. And the reason to do this like volatile read instead of just a normal pointer dereference is because this is like something that hardware can change. And so you have to like tell the Rust compiler like, yo, don't optimize this write out. Like, don't assume that you know what you put there like 2 seconds ago because someone else could be changing it. And that's hardware. So we say read volatile. And let's say cap length is cap length. And all of this is going to have to be unsafe because Rust doesn't like it when we interact with memory directly. He's like, hey, you dumbass, like you're going to fuck it up. So if you put the word unsafe around it, then you won't fuck it up. Okay, so he says, oops, let's take off this. Cap length 32. So what we should now hopefully see is after those 32 bytes, maybe we find these like values here. Because here they said the operation registers are found after the capability registers. So then we say let op, like regs, we'll call them regs for registers, is the cap length add, sorry, this should be range start add cap length. Zig handles this unsafe thing better, I believe, but I could be wrong. Yeah, I guess it depends on like what you think that it should do. Like, I mean, I was like clowning on unsafe, but I think it is pretty reasonable to say that like, I think that Rust's guarantee is like, if everybody wrote their unsafe code correctly, when you write safe code, you should never hit memory errors, right? Like you should never have like seg faults, and that type of thing, or like buffer overflows, or like, you know, stack corruption stuff. I think it's like a pretty, it's, I was clowning on it, but I do think it's like kind of reasonable. But I don't know what Zig does. I've never written Zig. I think I've heard that like Zig is like Rust for C and Rust is like Rust for C++. Like a much simpler language, but still getting some of the like benefits that you want from C++, like the like scope guards and like defer and like go like, I don't remember if it has like garbage collection. I don't know. I've heard it's like updated C essentially, but what do I know? Okay. Operation registers. These look like they're all 4 bytes long. So I'll just say that this is as a U32 pointer. And I guess we'll just iterate through each of these and we'll say 0, 4, 8. I guess we'll just, maybe we'll just paste these numbers in. That seems kind of nice. So we'll just do copy. And maybe we'll do like a little Rust macro to turn these into something. So we'll say regs add 0x this as a U32 pointer is going to be this thing, but lowercase, and back up by one. I wonder if that's... Oh, I love it when the Vim macros feel right. Oh, baby. That's so sick. And then I guess I actually probably want to dereference each of these. So we'll say... just put a star in front of it. Okay. And then I can just print all of these. So we'll say... we'll make another Vim macro. We're going to say info. This guy is himself. Okay. And I guess these things that we're checking against are written in hex. So we're actually going to want to put these as hex strings. Very cool. And now if I cargo run this, do I see something that looks kind of sane? Okay. Oh, wait. Those actually look like they might be right. USB command 80000. Yeah. USB stust, whatever that is, status 1000. USB inner 0. FTR index or FR index. This is wrong. That's concerning. Control segment 0. Config flag 1. Port 1000. So I think what does this tell us? The fact that the USB command and status are exactly what we expect, it does make me think that we found the right address of memory, right? That seems like very likely. And so my like theory maybe is the wrong word, is theories are like fairly strong. Hypothesis is that somebody's interacted with this controller before. Like just maybe in our BIOS to enumerate devices or something, or maybe like multi-boot, like in Grub, in like the bootloader, maybe they are touching USB, right? Like you could imagine that Grub, if it was going to boot from all devices, like it might want to read USB drives, right? Like if you have like a USB drive plugged in, like it would have to load like a FAT32 driver to know if there's like a thing to boot over there, right? So you could imagine that like somebody's interacted with this thing in a way and changed some of the default state. So it would be interesting if maybe we could like reset the controller and like prove that to ourselves. How do I do that? I wonder if I can do that like with QEMU. Oh, after initial power on or HC reset in the USB command register. Okay, so maybe I write host controller reset. So if I just write bit 1, so we'll do this. We'll say USB command reg is this. And if I say USB command reg write volatile, what was it, bit 1? So that's 0x2. That should make it reset if I'm just like randomly guessing, right? So now let's like sleep for some amount of time. So we'll make this like an async function that takes in the stuff that we need to sleep, like a reference to the time and shit. So we'll say what? We take in the time as a monotonic time and a wake up requester as a wake up requester. Okay. Which means that here in main, here I pass in the monotonic time and the wake up requester. And then here I should be able to say sleep, create sleep for, 10 milliseconds using our reference to the time and our reference to the wake up requester. And I would like to await that, please. Fuck. But now, like, our async stuff isn't, like, available in this context. Which is fine. That's fine, that's fine, that's fine. I'm just gonna have to stash this, like, PCI device. So instead of making this a free function, we're gonna make this a struct that we can, like, reference later. Who takes in his, like, device address. Cool. And then we're going to make impl ehci pub function probe, which is going to take in self by reference, as well as this other shit. And we'll just do all of this at that point. And the reason to do this is then I can, like, move all this code into, like, a demo section of the kernel. Okay. Which means that here we need to write and mute self, of course. Of course. Need it to be mutable. And then here we say our ehci driver does not exist until we find it. So then we say ehci is equal to ehci new. And we pass in the device. We make a public function new to construct it. It takes in the device, which is a general PCI device, and he returns ehci, and then we say ehci. Dude, I'm gonna misspell this every fucking time. I guarantee it. Okay, cool. So then we say this guy gets put in a sum, and here we say ehci is equal to ehci.expect failed to find ehci controller. And then we pass this into the kernel. We stash it for later. I guess this guy should go, like, down here somewhere. I don't know. Fuck it. And here we say ehci is an ehci. Oh my god. I'm going to say ECHI every goddamn time. And then in our demo, we can say we now have, like, a thing to do. So we'll say let ehci probe is an async block. And he says self ehci probe. And he passes in self.pci, the time, and the wake up requester. Cool. Does that all check out? Close. 282, I forgot an equal sign. Does that all check out? Close. Fuck. ECHI, EHCI, every goddamn time. I've actually done it again here. Okay, we're chilling. And now here I just type await, and then here I need to make one of the things I do. This, like, EHCI probing shit. It doesn't like that because this async block is not send, probably because of something. Oh, because this guy has this, like, fucking await shit. Ugh. Can I just say, like, dude, this is so frustrating. So the problem is that, like, I've, like, stashed some pointers, and Rust goes like, hey, pointers, those are dangerous, man. Be careful. And so it's saying, like, hey, if you have, like, a pointer to something, like, I can't guarantee that that's safe to be used for multiple threads. And so usually the trick is to, like, wrap them in something that is safe to be used across multiple threads, which is, like, a pain in the ass. I might be able to, like, put this in a scope. Just, this is my workaround. Don't judge me. Uh-oh, did I crash? Am I back? Yep, we're back. We're back, baby! Okay. See, yeah, so now that I've like put this in a scope and then moved it over here, now it goes like, oh, pointers aren't used across a weight boundary, so it's safe now. And it's like, okay, shut the fuck up, Rose. Like, I get it. But let's run it and just see if we see something different. Right? I'm kind of hoping that by resetting the controller, I guess I probably actually want to do this in both cases. I just want to see if it changes. So here I do this. And I want to see that in the 10 milliseconds that I wait, I see different values. Hey, look at that. Let's go, baby. So here I do see that like these things that were in the wrong state before, some of them, I think that they've been reset, right? Like this FR index was at 0x30 and now it's at 000. Which is a really good sign that just what we did was what we wanted. Pretty sick. Pretty sick. So I think that's where I'm going to call it for today because we're kind of like just about 2 hours. I like to kind of keep these kind of short-ish because if I make like a 7-hour video, I think nobody in their right mind would ever watch that. So it's kind of nice to keep it in like 2-hour chunks. That's kind of like the limit of where I would want to watch. So thanks for watching. We kind of got a fair amount done today. I think that we're still pretty fucking lost in the terms of like what EHCI is going to look like, what USB looks like. But we are kind of in like a pretty good state where we've at least proven that we found the controller, and that we can like interact with it in a way that like we kind of know what to expect. And so probably the next steps are going to be like, now that we like have a handle this controller and we're like pretty sure that we know where it is, how do we like ask it to do the things that we want it to do? We've done like some amount of reading, so we've got like a bit of an idea, but not really like a good enough idea to have done it yet. So probably next stream, I'll probably just come in and just start trying to poke and see if we can find a device. That's probably the next step. If you like what you saw, I stream most days around somewhere between like 1 and 2 o'clock Pacific time, and I go for like somewhere between 1 or 2 hours. And if you miss stream, there's a YouTube link in the Twitch description, so you can catch up. All VODs go up to YouTube eventually. And if you're watching on YouTube and you want to pop in and say hi, there's a Twitch link in the YouTube description. All code is available on GitHub, so if you want to go poke around, my username is my GitHub username. They all three match. So you punch it into GitHub, you should be able to find it. Yeah. Thanks for watching. Catch you on the next one. Bye!